everyone. I'm happy that my bell was effective, my deafening bell. So welcome to day number 2 in the proof workshop. This morning, the morning session will be a morning session of talks given by practitioners. Okay, and we're very excited to start with Hadas' talk on error correcting codes and its application to efficient SNARKs. Woo! Woo!
Thank you, everybody, for coming. So yeah, my talk today is on error correcting codes for efficient SNARKs. Okay, so as you guys know, the topic of this workshop, partially, is succinct non-interactive arguments of knowledge, where we have a prover and a verifier. And the prover wants to prove that it knows a witness that satisfies some circuit with respect to some common public input. And we want the proof to be succinct, and we want it to be non-interactive. Okay, so why SNARKs from error correcting codes? So there are 2 reasons people want SNARKs from error correcting codes, and one is that they have very fast provers, and that's the main reason that you'll see these being implemented in industry a lot. So the prover computation consists only of finite field multiplication, finite field addition, and hash functions. And hash functions are maybe not inherently super fast, but there are a few that have been highly optimized for commodity hardware, and so they can be very fast to run. Blake 3 is one of them. And then the other thing compared to elliptic curve-based SNARKs is that the fields don't have to be cryptographically large. So you can have some like pretty small fields, sometimes very, very small fields. And then the other thing is they're plausibly post-quantum secure. So the only security assumption is the collision resistance of the hash function. And then, of course, we're in the random oracle model. So maybe that is a big assumption, but mainly it's very simplified assumptions. And that's also interesting to some people in industry. Like, for example, Signal has been upgrading all of its systems to be post-quantum secure. And they actually use zero-knowledge proofs in their group messaging. So they are looking into this as well. Okay, so what is an error correcting code? So let's imagine for a second that you live in a country with a very bad postal service, but nonetheless, you want to send a message to somebody. And so let's say it goes on a really circuitous path and it has to go through a bus, a boat, a bike, and then finally it gets to its destination. And maybe in the boat, water splashes on it. So you get the letter and all the letters are smudged out. Well, English has this beautiful property such that where even if a bunch of the letters are smudged out, you can still understand what it's saying, usually. And so we hope for that also in our digital communication. So error correcting codes really started because we're sending strings of bits to each other all the time over noisy channels. And even if it's corrupted, we want to be able to recover the message. Okay, but why for SNARK? So in this situation, we're not talking about noisy channels. We're just talking about SNARKs with potentially malicious provers. Okay, so if I'm a malicious prover, or if I'm somebody that just wants to lie and I don't know how to tell the truth, I might benefit from just kind of saying something ambiguous and hope that it kind of looks like something that's true. And so that would be the strategy that a prover would use. It would kind of output a string and have, it would be sort of ambiguous as to where it is. But if you're using an error correcting code, you won't be able to do this because we have something called the proximity test, where you can actually test how close a vector is to a code. And so if a prover was super ambiguous, the verifier would reject. And if it's not, then actually it can be bound to some witness, and so the prover might accidentally become an honest prover, or it will be bound to some witness that is totally nonsensical. So using error correcting codes, that's just very hand-wavy and high level, but this is sort of why we can expect to get something from. Okay, so linear error correcting code is, we won't be using any nonlinear error correcting codes. So the definition of a linear error correcting code is a k-dimensional subspace of f to the n. We have that so you'll have a message of length k, and then you'll encode it, and you'll get a message of length n. We need k to be strictly smaller than n, because if k is equal to n, it's a very bad code, meaning that basically what we want is that the vectors in the subspace are far enough apart from each other. And so we have this global property on the code called the minimum Hamming distance, which is the closest that 2 vectors could possibly be to each other. So if k is equal to n, these guys would be like touching, and that would be bad. So we need k smaller than n, so we have some space between them. And then another important property of the code is the rate, which is the message length over the block length. So k over n. And we'll often be looking at the generator matrices of the codes. So in a linear code, the encoding algorithm can always be described by a linear map. And so it can be described by a generator matrix. And then encoding is just M times G. And that will become useful. And I'm sorry if anybody prefers G times M. I've heard that this is a thing that bothers people, but I'm left-handed, so I tend to put things on the left. OK, so the rest of the talk will proceed as follows. First, I'll go over preliminaries, just describe the different definitions of, well, really motivate and define interactive oracle proofs and interactive oracle proofs of proximity. I'll touch briefly on the paradigm used to build SNARKs from error correcting codes. Then I'll jump into, and I'll describe IOPPs in a lot of detail, which are interactive oracle proofs of proximity. Then I'll jump into properties of SNARK-friendly codes, a very small zoo of SNARK-friendly codes. Think of it like the Central Park Zoo, where they don't have a lot of animals. And finally, existing trade-offs and open questions.
That's a question.
Yeah.
In what sense? In some sense, I feel like almost all the SNARKs are based on error correcting codes, because how do you shrink? The idea of to shrink is like basically you do some form of an error correcting code on your proof or on your witness, and that's how you get it simple. Oh, I.O. Okay.
Well, well, there is another sense of how error correcting codes are used in a way that I don't touch upon, which is the sum check protocol is often behind SNARKs, and that is using Reed-Muller codes behind the.
Exactly. That's my point. Almost all of them, except for I.O., have like an error correcting code in there.
You're right. Yeah, you're right. I would say that this is the class where like they become a huge bottleneck, because like in SumCheck you don't have to worry about encoding time of Reed-Muller because it's all sort of virtually there. You only send like small messages. But yeah, I think that's true.
The other thing, I think you're biased towards what people call hash-based SNARK, where there's a different class in which you do like fancy things with like the discrete log, and you're not like explicitly encoding maybe. Sometimes behind the scenes they're not explicitly they're polynomials, and you do read some encoding, but it's somewhat less direct than I would say the usual like hash-based thing that you think of, like a PCP-based thing.
Yeah.
Yeah, okay, that makes sense. I'm also biased towards those. So. Okay, so first, interactive proof. So why so many interactive proofs? Well, in a nutshell, interaction makes it harder for a malicious prover to cheat. So a nice analogy I like is a very nervous student taking a test. So if I'm a teacher teaching a class, I don't have time to listen to every single student tell me everything they learned in that class that semester. That would take forever. So instead, I choose not randomly selected questions, but hopefully unpredictable questions that the students can't guess in advance. And then I see how well they do on it, and that should give me some probabilistic guarantee that the student knows what I taught in the semester. So it's defined formally as an interactive protocol between a prover and a verifier that operates over several rounds. In each round, the prover will send a message, the verifier will respond with some randomness, and the prover will send another message. This can go on for as many rounds as needed, and then eventually the verifier either accepts or rejects. And then another notion of proof is a probabilistically checkable proof, or a PCP, where in this case it's non-interactive. The prover will just send a very long message to the verifier, and you can think of it as sort of existing in a database that the verifier has access to. It doesn't want to read the whole thing, so it'll just read some of the elements. And so it'll read some, not all of the elements, and then either accept or reject. And then really the main character of this topic is interactive oracle proofs, which are a combination of these two things. So it operates over several rounds, like an interactive proof, but like a PCP, each of the messages are very long, and the verifier won't read them in their entirety. So this will happen, and then the verifier will query them at some number of points, usually a constant number of points for each oracle, and then either accept or reject. And then just quickly to talk about the general SNARK paradigm, they're built from a type of IOP called the polynomial interactive oracle proof, where now instead of sending, or it's just a more specific, where the oracles are polynomials and the queries are evaluation queries for polynomials. And this will also operate over several rounds, at the end of which the verifier will accept or reject. And this is instantiated with the polynomial commitment scheme, which we saw yesterday, and this is the first cryptographic object I think I've discussed so far, but the prover will send a short commitment to a polynomial, get back an evaluation point, and then send the evaluation and the proof. And the verifier will accept or reject. And there's a notion of knowledge soundness, where if the proof or strategy is accepted with non-negligible probability, then it's possible for a polynomial time extractor to extract a unique polynomial from the commitment satisfying the evaluation. And the paradigm for building this is you'll take a polynomial IOP where the prover is sending polynomials, and you'll instantiate it with a polynomial commitment scheme. So the prover is not actually sending polynomials now, they're just sending commitments to them. And together you make a SNARK. I'm not really going to discuss that here, but just so that we know where we are. And then the polynomial commitment scheme itself is built from more interactive oracle proofs. So an interactive oracle proof, and then which comes from an interactive oracle proof of proximity. Any questions up to this point? I'm going to now dive into interactive oracle proofs.
Maybe this is a bit out of scope, but like, you know, if there's any like place where interactive oracle proofs are used without like commitment, just like plain interactive oracle proofs, or are they mostly just this like thing that you usually put inside a commitment?
I think you always, that I know of, put it inside a commitment for two reasons. One is the interactive part, so we don't really like interactive protocols, and the second is the huge messages you're sending. But does anybody know differently?
Maybe add that in the special case of a one-round interactive oracle proof, it's called the PCP.
Yeah.
And this is, used for like the entire field of hardness or approximation.
Yeah.
Right.
But
Yeah.
that's sort of very different.
Yeah.
Yeah. Right. That's true. That's true. Thank you. Okay. So an interactive oracle proof of proximity is another special type of interactive oracle proof. But now the statement we're proving is very specific. The prover has a vector and wants to prove knowledge of a vector, such that the distance between the vector and the code is small. And by distance from vector to a code, so far I've just talked about distance between two vectors. So when we talk about distance from a vector to an entire code, we mean the distance from a vector to its closest code word in C, breaking ties arbitrarily. And so this operates just like, this is an IOP, so it operates in the same way. Although we call the first part the commit phase, and the second part the query phase. So in the query phase, the verifier will query. All right, so this is just a 3-round version. Actually, you can do many rounds, but just to use a 3-round version to simplify it, the verifier would query a constant number from the first oracle and then read the second oracle in its entirety. I'm not sure if the color contrast is showing up that much there. It is? Okay. And so the idea is that the verifier will query the first oracle at a constant number of points. It will read the second thing in its entirety, and then it will check some predefined linear relationship between these two, and it will check that the final oracle is a code word. It can just check that directly because it read it in its entirety. And the principle underlying why like this, or like what the soundness of this will be, is the fact that we will show later that if these linear relationships are satisfied, and the last thing is a code word, then the first thing is a code word. Like that is something that we will have to prove. But that's the main idea behind the proximity test. And so we have completeness and soundness. So similar to other proof systems, a verifier accepts an honest prover's proof with probability 1, and then soundness would be if the prover sends an oracle that is far from the code, then the verifier accepts with negligible probability.
So what you're explaining here is a proof of proximity, not a IOP of proximity.
It's a IOP but it's an interactive oracle proof of proximity.
But then you don't read everything. So there's the proximity part, which is what's up there.
Yeah, I see you mean because of the final thing, right?
And then there's the proximity part, which is up there. They just read a few locations.
Yeah.
And then there's the interactive oracle proof or interactive proof, whatever it is. Now, if it's an interactive oracle proof, then in that part also you read a few, unless you commit, and then it's not an oracle proof anymore because you cryptographed it to an interactive argument.
Oh, I see.
So either you think of it as an interactive oracle proof, in which case in every round you read a few locations because it's an oracle proof, or you compiled it already, in which case it's now an interactive proof.
That's true. I guess the way I would describe it is in these specific, I guess I'm talking about a very specific instantiation that like started with Fry and like comes down from there, where the definition is still reading some number of points, but then you get the last oracle so small that you can read the whole thing. And so you just generalize the number of points for just the last oracle to the entire thing. Like you can read, it gets to be like a constant
Okay, but for
size.
those who don't know what phi is, how should we think of it? Should we think of it just as an oracle where you read a few locations and then you verify proximity of the statement?
Yeah, I would think of it as an oracle group where
statement?
you're reading like a few locations. However, for the last oracle, you just read all the locations.
Okay.
Yeah, so everything's an oracle.
The last thing is not an oracle, basically.
You're right. The last thing is not an oracle. Yeah, the last thing's not an oracle, or it's an oracle where you queried everything. But yeah, that would be nonsensical. So that's a good point. Okay, and then you can have more rounds. So so when you have what I described in the 3-round protocol, you're right. Like the second message will be quite long, but if you have logarithmic number of rounds, you can basically make it that the last message is really like 4 field elements or something like that. So it's sort of too small to be an oracle at that point.
Okay, but that's a specific.
That's a specific
that you're
IOPP.
talking about.
Yeah.
It's not a general definition.
Yeah,
It's like-
you're right. That's a specific IOPP. Yeah. Okay, so then we're going to make it non-interactive, which was,
Yes. As a building block of a polynomial commitment scheme, where do you get the evaluation guarantee?
oh yeah, I'll describe that in a second actually. But basically these specific classes of IOPPs can be also seen as interactive oracle proofs of random evaluation. And then from there you can get a polynomial commitment scheme. But I'll discuss that in a second. But I mean, generally, yeah. Okay. There's different ways depending on how you do it. Okay, so non-interactive, we discussed this a lot yesterday, so I'll go over it quickly, but we have a Merkle tree, so we have our long oracle, we put it into our tree, we get out a root digest. Okay, now we do the Fiat-Shamir part, so we put the root into a hash function, and we get out the verifier's randomness. So there's no verifier yet here. Okay, the randomness gets sent to the prover, and the prover will output its next oracle. And then we do Fiat-Shamir again, like we'll get a transcript from here. We'll do Fiat-Shamir again to get the random queries. So now instead of the verifier choosing queries randomly, it will come out of this hash function. And the prover will make Merkle authentication paths, which are like vector commitment proofs, which Ale was talking about yesterday. And yeah, so then what the verifier has at the end is a set of Merkle authentication paths and a final oracle. So this is the proof. And the verifier will check the vector commitment proofs, and it will check the same things it checked before. Any questions about that? Okay, great. Okay, and now going to your question, Ali. We can actually, so it was observed in a couple papers that this class of IOPPs are actually also IOPs for random evaluation and of a multilinear polynomial. And the reason is that the linear relationships I was talking about before that these two oracles satisfy, they end up being equivalent to multilinear, like partial multilinear evaluation each round. So you can see, for example, the top one as encoding the coefficients of some polynomial, and then the next one encoding the coefficients of a partial evaluation of that polynomial. And then after enough rounds, you'll get an encoding of the full evaluation of that polynomial at a random point. And it's sort of well known that you can use the sum check protocol to reduce arbitrary polynomial evaluation to random polynomial evaluation. And I think there are other ways to do it as well. But basically, that's at a high level the way that you can get PCS from these IOPPs. Yeah.
Sorry. So IOPP, I think, from my understanding, the main difference between IOPP and IOP is the soundness guarantee. That the soundness guarantee doesn't say your input is in the language. It says it's close to the language because nobody actually reads this input, right? You can't hope to say it's no. Okay, so it has this kind of weak, quote unquote, form of soundness.
Yeah.
Okay. Now you're saying I can use an IOPP for some language, I'm guessing, to get an IOP for random evaluation.
Yeah, you're right. That's confusing. I'm mushing definitions. I guess the motivation, the reason I think of it that way is because it is an IOPP, and those, I mean, I guess you can view it as both. It sort of does double service. Like if you wanted to just use it as an IOPP and just prove the proximity, you could. Or without changing anything, you could also prove this other thing. So I guess it proves both.
Well, what is your input? When you think of an IOP, what's the input to the IOP?
Yeah, right. The IOP, right. So the input would be, I mean, like, okay, but it's a specific IOP for proving evaluation of a polynomial. So your input would be a polynomial. Yeah.
And everybody reads this polynomial. Like it's an input, so you have to know that.
It would be an IOPP, so the input is a kind of encoding of polynomials. And your goal is to prove that the oracle is close to a code word, that is the encoding of polynomial sets. This polynomial satisfies this certain evaluation.
Okay, so the input is not the polynomial itself, it's an encoding of the polynomial.
Yeah.
And then you use the locations.
Yes.
So it's also a proximity.
Yes, yes.
Oh, okay. So you're doing like an IOPP for random evaluation.
Oh, okay, that's a better way to
now I
put it.
understand.
Thank you.
Got it.
Cool. Yeah. So. Yeah. Okay. So that concludes that section. So now we're going to go through the properties of SNARK-friendly codes. Okay. So we remember this slide, right? This was the whole shebang for a prover. Okay. So now I'm going to point out where do the prover costs come from. So the first thing, which is obvious, is the encoding time of the code we are using. An honest prover will have to encode the whole message for its first oracle. And that ends up being the biggest bottleneck because it's the longest. All the oracles after that one are smaller and smaller, and so encoding them will be cheaper, or creating them will be cheaper. So the encoding time of the code has a huge impact on the overall prover time. And then the second thing is the time to prove the linear relationships between oracles. So sometimes that's as simple as just encoding a smaller thing, and sometimes it's more complicated than that. And so that can also have a big impact on this. And then the verifier costs are almost entirely determined by the number of Merkle paths you get, because that will determine the verifier time and the proof size. Merkle paths are actually not very cheap because they're log n hashes, and each hash is 256 bits. So you're already starting from a bad place when your hash is your basic unit of counting. So what we care about is how is the number of Merkle paths determined. So it's by the minimum distance of the code, and then also the best soundness analysis available for that code. So some codes we have tighter analyses for, meaning at a high level, what is the furthest the vector can be from the code so that bad events that could allow a malicious prover to win still rarely happen. And Reed-Solomon codes have the best analysis for that, so they'll tend to perform better for proof size. Okay, so to summarize, the prover costs are encoding time, which is influenced by encoding algorithm of the code, and also field choice, which I haven't mentioned yet, but I will mention later. And then the cost of proving the linear relationships between subsequent codes. And the verifier times are the minimum distance of the code and the best soundness analysis for a given code.
Okay, so maybe high-level things. So, Merkle things are only relevant for things which are based on I guess just reading physical positions, but I thought you were talking about polynomial commitment schemes. Are they relevant for polynomial commitment schemes?
Well, we're deriving our polynomial commitment scheme. There's like a reduction from polynomial commitment scheme to this IOP, to this IOPP, where Merkle paths are still the bottleneck in the proof. So we will basically compile this into a polynomial commitment scheme, but the main proof size still comes from the IOPP.
Okay, so you're building a polynomial commitment scheme, but from things which read physical positions.
Yeah, exactly. Yeah.
So you have to encode the code of the hash function of the Merkle tree, right? Inside the encoding.
You have to hash the encoding of the message.
Yeah, but when you reduce it to the polynomial commitment tree, you have to encode the code of the hash function into the message. Well, for the path, right, to go down.
No, because it's just the verifier doing that. So
Right, but, I see. So you give it explicitly or you encode it?
No, you just give it explicitly
I see,
in the
okay.
setting.
But then you might on top do a recursive proof.
Yeah, you could do recursive.
Recursion.
So then you need to encode
If you do
the
recursion on top.
actual code of the hash function.
And that's actually why recursion is often not, like it's often very expensive. It has a lot of overhead because of that, proving hashes. But this is not recursive. This is just, I send you my Merkle paths and you verify them. And hashes are CPU friendly. Okay, so now cost of proving linear relationships. There are sort of three classes of codes that determine how you do this. So one is an interleaved code, and then a foldable code, and then a code-switchable code. So a code that's amenable to code switching. Okay, so an interleaved code is kind of like a very simple thing. You have your messages, you break them up into chunks, you encode each chunk, and you get a bunch of code words. And you can do this with any linear code, any linear code at all. So you can pick the fastest one. And it just nothing really. They just why is it called that? You mean? I think just literally because it's just because they're rows. I think it's supposed to be like halfway to a tensor code, kind of like instead of
every
encoding
column
rows.
of the matrix is a symbol. Right? a column of the code word matrix is considered the symbol, so you interleave the symbols in different
I
codes.
see. That makes sense.
It's not, the terminology comes from coding theory.
Okay. Okay. That makes sense. Thank you. Okay, so there's a simple IOPP for interleaved codes where the prover sends a code word. The verifier sends back randomness, a vector, and then the prover will take a linear combination of those rows and send that. Then the
M's are code words, right? Not messages.
Oh yeah, sorry. The M's are code words, not messages. So the verifier will check a constant number of columns and then check that it's consistent with the last thing. And then the idea is that if the last thing is a code word and enough of these columns are correct, then we can assume that this last thing is a linear combination of all of these, and that should imply that these are all code words, or close to code words rather, close to code words. And yeah, sorry, there's a mistake on the slide. Those should be, or just pretend M stands for code word instead of message. Okay, and then there's a foldable code, which is a neat class of codes that sort of are kind of like interleaved inherently in a sense, if you wanted to use that terminology. So in a foldable code, you can imagine that you have two sides of a message, and now you take pairs of points, and each pair of point will be mapped to 2 points. So these 2 points will, so A and B are field elements. They're symbols of the code. And then the subsequent elements will be A plus T1B, A plus T2B, where T1 and T2 are some field elements. And that will encode M0 concat M1. So basically, this is sort of an abstraction of an FFT. You get two, if you're familiar with an FFT, that might be helpful. If you're not, forget that I said that. But you basically have two encodings of things, and you can sort of do a convolution type thing and get something that is larger.
What's the size of that bigger thing?
So it's two times the size of one of the individual things.
Just two constants, T1 and T2?
Yeah.
Just kind of.
Yeah, exactly. And they do matter what they are because that impacts the distance of the code, but for the intents and purposes of the slide, it's just any constant. Okay, so then IOPP for foldable code, which is a generalization of Fry. If you've heard of it, it's a paper from 2018 that sort of got this area of practical SNARKs started. So the approver will send an oracle to a foldable code. The verifier will just send a random field element. And then the prover will create a new oracle where every element is A plus RB, where R is the same across the elements. And so what this does then is, what it does is this thing ends up being the linear combination of the two messages underlying the top thing. And unlike in the interleaved case, you can continue now. This is also a foldable code. So if you are familiar with FFTs, this is kind of like an inverse fast Fourier transform, but in an interactive setting, sort of. And so you get something that still has this cool structure, and you can just continue. And every time you continue, it'll split in two, and then, yeah, there'll be log rounds. And the verifier now can check these relationships by choosing a pair. Notice that the two pairs are evaluations of a univariate polynomial whose coefficients are A and B. So it'll interpolate and evaluate it at its own randomness R, and then check that that's consistent with the final oracle. And if so, it's convinced that this thing is formed correctly. It'll check that that thing is a code word, the bottom thing, and then there's a guarantee that that implies that the top one is too. And finally, we get to code switching. So sometimes you do an interleaved code, and then, oh, sorry. Yeah.
One more.
Okay.
So, one more.
I have animations here.
Yeah, that's right.
Okay.
So the prover sent you this A plus RB.
Yeah, the prover.
But in the next slide,
yeah,
you said the verifier on his own does this.
So they both can do it because it's totally local operations. The prover will do it for every single pair because they're actually creating a new oracle, and the verifier will just check it at a constant number of pairs. Another way to think of it is
so the verifier is checking that the prover did the right thing.
Yeah.
But the reason the prover is doing it is because that's costly, and you're in this mode where you don't read the whole thing.
Or sorry, yeah, the prover, you could just think of it as encoding the message M0 plus R M1, where M0 and M1 are like the two halves of the original message. Like it's just creating a new code word that's shorter. However, that is n log n time. So when you're we want this to be linear time. And so the prover does this more efficient thing also. So basically, you can create this new code word in linear time by just interpolating and evaluating each pair. Yeah.
So the verifier is local randomness. You also feature numerical.
Yeah. Yeah. Everything is fairly numerical.
What's the definition of this code? You can do any code take just linear combination of the two code words, so linear combination.
Yeah. The code is defined by the T1s and T2s. So basically, I'll describe this later, but when you pick T1 and T2, you could take any message and do it, but if you continue to do it over and over again, you basically end up with something like a Reed-Solomon code. So not any code. Most codes are not structured like this. And I kind of just broke it down into like the linear operations that underlie it.
The structure you end up with?
Yeah. What did you say?
Is it about the structure?
Yeah, it's with the structure you end up with. Yeah. I just showed you like one step of the encoding algorithm, basically. Like think about like if you know like univariate polynomial evaluation can be done efficiently with an FFT. I just showed you like one step of that FFT, basically, but in a general form. And yeah, does that make sense?
So what did you say is that after you do this operation, the code is still foldable?
Yeah.
So you assume that you recursively encode foldable code?
Yeah, so yeah, exactly. So, okay, I'll define this later. And, but basically when you define a foldable code, it should be many, many levels so that every time you do it, it's foldable. You could do it just one level, but then you won't get that much from it. And you could do it a few levels too. I guess, yeah, there's flexibility there. But I guess the cool thing about a foldable code rather than an interleaved code is you don't get stuck. You can just continue. So if you do an interleaved code, you kind of get stuck. Like your linear combination is not itself interleaved. Okay, so that brings us to code switching. So when you get stuck, you might want to now switch to a foldable code. So let's say we have a nice linear time encodable code, get stuck, switch to a foldable code. And the way we do that is like this. So you start with your first encoding under C of M1. And then you're going to produce another encoding of M1 under a different code, C star. And we want to prove that they're consistent with each other. Because our code is linear, our encoding algorithm is just vector matrix multiplication with the generator matrix G, which we kind of know how to efficiently prove as long as G and G star are well structured. So if G and G star were like random matrices, this would be very expensive. Still possible, but expensive. But if G and G star are well structured, in particular a product of sparse matrices, which I'll show later, then you can prove this efficiently. And so to summarize, an interleaved code gives you always the fastest proving time, but large verifier costs. A foldable code sort of gives you maybe best of both worlds. And then if you use code switching, kind of like the sky is the limit with how small you can get the verifier costs, because you can just keep sort of switching to better codes. And
before this, what is it you want to prove, that M and M are equal?
Yeah,
so you're giving like a commitment to MG and a commitment to MG star, and you want the prover to prove to you that they're both kind of committing to the same encoded M.
Yeah, the same M.
And now what you're doing in the next slide is efficiency of what?
This
or of
the prover time of the IOPPs that I just showed.
In general,
IOPP.
Which is
well, I guess it is the specific ones I showed for it. So like an interleaved IOPP here. Sorry. All right, let me be more specific.
That's a good point. What are you proving?
Yeah, what are we proving? Eventually, this will be compiled into a polynomial commitment scheme. And at that point, the prover time of the PCS will depend on the prover time of the IOPP. If you do an IOPP for an interleaved code, you'll end up with a linear time prover for the polynomial commitment scheme.
You're measuring things in field operations?
Yes. Yeah.
And communication does not appear here, but it's roughly...
So verifier is very hand-wavy. It encompasses verifier runtime and also the proof size. And the proof size is the Fiat-Shamir version of communication, basically. So it's like all the Merkle paths.
Yeah.
Okay, and now to the verifier costs. So okay, minimum distance of the code is self-explanatory. So I'm going to... Yeah, of course.
There was so much about it yesterday. So when you say it's Fiat-Shamir style, so this is all under the assumption the Fiat-Shamir works?
Yes.
And then you're only measuring the size of the first message?
Measuring the size of the first message? No, we measured the whole transcript after Fiat-Shamir.
Yeah, but you're saying with the Fiat-Shamir, so whenever you're doing the Fiat-Shamir, you don't count that communication.
Oh yeah, you don't count the whole message as communication. Yeah, so like
Merkle root of your communication.
Yeah, the only communication is really the Merkle paths and the roots. Yeah. Yeah. Okay. Okay. So now the soundness analysis for a given code. So So the way that we get soundness is you say if with high probability the distance of this linear combination of v0 and v1 is close to a code word with highish probability greater than epsilon, then we get this guarantee that the two constituent vectors v0 and v1 both agree with code words and at corresponding points, and that their linear combination is sort of the correct thing. So also agrees with code words there, and is a linear combination. So is an encoding of the linear combination of the underlying messages of the first two vectors. Okay, so this term here, so CL is the encoding of ML, or close to it. CR is close to the encoding of MR. C is close to the encoding of ML plus R times MR. So we get that guarantee as long as this probability holds. And that impacts the number of Merkle paths. So if you remember, number of Merkle paths is the size of the proof. It's the bottleneck. And basically, we need to make sure that the oracles are closer than delta to the code. So we need to make Q queries such that 1 minus delta to the power of Q is small. And so we're going to need Q Merkle paths. And delta is inversely proportional to the minimum distance. So we want the minimum distance to be as large as possible. And we also want delta to be large. So that depends on the soundness analysis. Okay, great. So now we're at our small zoo of SNARK-friendly codes, and we're ready to dive into the specifics. Okay, and I have till 10:30 or ish. Okay, awesome. Okay, cool. Okay, any other questions at this point? Yeah.
So switchable codes are better in all ways?
Oh, well, I would say the story is not that clear cut, and I'll show a little bit about that later. For smaller sizes, the prover overhead can be a lot. For larger, like message sizes, it's usually worth it, and it becomes better in every way.
Well, if you think of it as that if you compare to interleaving, you have like a square root n cost. So the small size, the square root is fine.
But the other one, you have log square.
Yeah.
Right. So for big enough n, log squared is better.
Or for, yeah, or that's talking about code switching, the proof size will always be better than interleaving, but the prover time of code switching, I guess, is the thing that makes it not always worth it, because there's overhead to that proof. Proving that m times g and m times g star are consistent is more expensive than, like in foldable codes, you just output the next oracle and you don't have to prove anything extra. So sometimes that makes it not worth it.
Is the epsilon like fixed, like the distance in the proximity?
Oh no, I'll talk about that later actually. It's not, and that is another source of trade-off. You can make epsilon bigger to make the probability better, but the queries worse.
Well, I was curious because like every time you fold, won't it like slightly increase?
Yeah, that's true too. Yeah, but there are tricks around that too, but I don't get that into that. And let's talk about that after though. That's an interesting trade-off area. Any others? Okay, great. So our zoo of friendly codes, our friendly zoo of friendly codes. Okay, of SNARK-friendly codes. So I classify these as foldable and not foldable. It's somewhat of an arbitrary distinction, but foldable codes do have certain kind of a lot of commonalities. So for under foldable, we have Reed-Solomon, which are classic from the 60s, random foldable codes, which is from a recent work of mine and Vinny's, and circle codes, which are another recent work. And the point of random foldable codes and circle codes are just to make them more field agnostic. So Reed-Solomon codes only work under certain fields, and these can expand that. And then under not foldable, we have repeat, accumulate codes, REA codes, and Spielman codes.
Are Reed-Muller also foldable?
Yeah, Reed-Muller are foldable, but they're not really practical. Although actually random foldable codes or foldable codes are like punctured Reed-Muller. So Reed-Muller restricted to certain coordinates. And I think they get the foldability properties from the fact that it's Reed-Muller. Okay, so foldable codes have quasi-linear encoding time and tend to have large distance. Not foldable have linear time encoding, smaller distance, but related to the linear time encoding, they tend to have efficient code switching. So we can kind of get around the fact that they're not foldable. And then, yeah.
It's really a very zoomed out thing. So it's like a religious preference to foldable? Why do I care?
Oh, why do you care about if it's foldable or not foldable?
Yes.
Oh, okay. It's related to what I was talking about before. So foldable, you get like this sort of efficient way to continue your IOPP for as long as you want until you're at a constant size. Okay. Not foldable is you don't have that structure, but there's ways around it, and somewhat religious preference, yes.
Because of the structure, the verifier is much more efficient
With foldable.
Yeah.
On high level, when would I want to use a foldable?
Because of the structure, the verifier is much more efficient.
Kind of get into. I think if you have a medium-sized message, you want to use foldable. And then as your message size gets larger, you would rather use not foldable plus code switching. It's pretty much that.
I also mentioned that foldable codes are also very efficiently code switchable.
Yes, they are. Yes, true. Giacomo makes a good point. Your work. And it shows that, yeah, foldable codes are very code switchable. And in fact, you could kind of see foldability, I guess, as a subclass of code switchability. But like, I actually thought about that, and I was like, should I just put them under the same umbrella? But then I thought, no, foldability is like there's too much there. I think I'll just separate it.
So when we're during the switching curve, non-foldable, or are we switching between these two categories?
So you're usually switching you're gonna always switch from not foldable to foldable, because you want your most expensive thing will be the top message, the first one, and you want that to be in a very fast code. Okay, but then you're gonna get stuck.
A few rounds of the non-foldable, then switching to foldable.
Yeah, exactly. Yeah, exactly. Okay, so then further classifications of foldable, but I'll go through these quickly because we're short on time. So field agnostic, somewhat field agnostic, FFT friendly. Okay, well this is kind of cool. So foldable codes can all be described with a generator matrix that looks like this. So it has a recursive construction. You can start your G0 with anything you want, but simply it's easy to think of it as a repetition code generator matrix. And then you can, each round you build it like this, where TD and TD prime are diagonal matrices. And yeah, so they all have this code structure. So basically, like in the first round, you would take G0, you copy and paste it on the left, copy and paste it on the right, put it on the bottom times some diagonal, put it on the bottom right with a different diagonal. And that is the structure of a generator matrix of a foldable code. And so with that in mind, I can now describe quickly the different foldable codes, because they differ just in how the diagonal matrices are sampled. So we have a random foldable code, they're sampled randomly. And we proved that that has pretty good distance. Reed-Solomon code, which is like an FFT, the diagonal matrices, at least over primes, it's more complicated over fields of characteristic 2, but at least over primes, the diagonals are roots of unity. And then circle codes is a recent code that was built to make this possible over Mersenne primes, which have nice, like really fast modular arithmetic on CPUs. And so that just uses a different group, like an elliptic curve group. And so these are just group elements. And so all of these. Okay, sorry. Okay, so yeah, a circle code it's like a Reed-Solomon code. It's Reed-Solomon-like, but the diagonal matrix is group elements. The group is some elliptic curve over addition for certain nice curves.
Are you working over these? You're not working in a field anymore?
Oh, you're
so asked about the arithmetic you're doing now.
Okay, yeah.
Typing of these variables is confusing. How are you doing arithmetic?
It's just elliptic curve, like arithmetic. So
you need a field.
It is in a field, yeah. But it's not in an FFT-friendly field. So you can use any field whose prime is.
Wait, circle codes use circles, not elliptic curves.
Oh, they use circles.
Not elliptic curves.
Oh, okay. Oh, I thought it was still a type of elliptic curve, no?
X squared plus y squared equals.
Over C.
Oh, okay. Sorry.
Okay.
Yeah, sorry. I admittedly don't know. I'm not an expert on these codes. I thought that it said that it used elliptic curves.
It's like a curve.
Yeah.
Use functions over the curve.
Okay, so anyway, they work over prime fields whose modulus is equivalent to 3 mod 4, which encompasses like all Mersenne primes. So Mersenne primes are 2 to the n minus 1, and they're fast. You can do fast modular addition that way. Okay, so circle codes and Reed-Solomon codes both have like the best possible distance. Random foldable codes have pretty high distance with high probability. And then Reed-Solomon codes have better proximity gaps. And sorry, I miscited these. These are just like the most recent results for the multilinear setting, but I know proximity gaps of Reed-Solomon codes is actually the paper that proved this in the univariate setting. And yeah, so Reed-Solomon codes have better query complexity. They have a better analysis, and that's possibly true for other codes as well. It just hasn't been done before. The other result is for all linear codes, and it has better probability but a worse query complexity. Okay, so let's skip these, but just practically, why do we care about fields? Like usually you don't actually care about what field you use. You can just use a Reed-Solomon code. But sometimes if you want to do specific applications, then you might choose a field that, for example, is like native to like a signature application you want to prove. And then you can use a random foldable code for that. Or you want to use a Mersenne prime field, and then you can do really fast multiplication, so you can use a circle code. And then, or if you want to do like an extension field with small characteristic, again, you can use a random foldable code. But if you want to prove something in a binary extension field, you can use Reed-Solomon codes. I was thinking of doing like a flow chart, like what Alex did yesterday, but it got too complicated. And then actually, most people just use Reed-Solomon codes at the end of the day because they're very versatile. There's like decades worth of optimization on them. So usually use a Reed-Solomon code, but if you have specific applications, you can use a circle code or a random foldable code. Okay, so now we'll get to the not foldable codes. So these are all code switchable. I'll be positive and not call them not foldable, but rather efficient code switchable codes. So they're linear time encodable, and they're code switchable because they're either or both a product of sparse generator matrix, or they have a sparse parity check matrix. And we have two codes in this family, repeat accumulate codes and Spielman codes, that at least that are sort of in the SNARK literature. And REAs over binary fields, and Spielman codes can be over any sufficiently large finite field. They both have probabilistic guarantees of distance. And just to remind you what code switching is, before I describe why it's good at code switching, it's when we want to prove consistency between these two things.
But why do you restrict REA to binary fields? And they can be generalized too, right?
Well, I guess we don't have a distance analysis for that.
Yeah, but you can empirically play with small parameters and see how they
But it looks like from experimentation, the small parameters don't tell you the real story.
In general, in codes, you expect that when the field size grows,
it's not smooth and the small.
Sure, but I think it's extremely unlikely that they are worse over bigger fields.
Should be better, but we don't have the analysis.
Well, we might soon. That's a good point. I think that analysis might be underway, but we don't have it yet. Okay, so repeat accumulate codes. This is a beautiful picture of the encoding of REA codes, where it happens in 5 steps. You start with your message, you repeat it, you do repetition code, and then you permute according to a random permutation, and then you take a prefix sum. A prefix sum is where every element is the sum of all the preceding elements. Then you permute again, and then you take another prefix sum, and you have your REA code. So it's very fast encoding. And also, related to that, it can be expressed as the product of some sparse matrices. So a permutation matrix, an accumulation matrix, another permutation matrix, another accumulation matrix. Permutation arguments are there's a lot of them in the SNARK literature, so we can just use one of those. Accumulation arguments, there aren't, but they turned out to be a simple sum check protocol. So code switching is relatively efficient here.
What's a permutation argument?
It's an argument where you have two messages as your input, and you want to prove that they're permutations of each other.
You're switching from which code to which code?
So I haven't described that yet, but yeah, this is based off work where we switch from REA to Reed-Solomon, so that we can continue the folding. Yeah.
What are these arguments?
Oh yeah, like an argument to prove that something is an accumulation of something else. So like you have the output of the accumulation, like the output of the prefix sum, the input of the prefix sum, and then you prove that that there.
So your code switching argument is a composition of these arguments.
Yeah, exactly. Yeah, exactly.
Wait, so you said this is not yet the switching itself, it's like the code?
This is the structure of the code that enables efficient code switching. And then the labels on the bottom, admittedly, confusingly, are the ways that you would then code switch.
Okay.
Yeah. And then Spielman also is the, I didn't get the citation right. Spielman is also a product of sparse matrices. It's a product of logarithmic number of sparse matrices, but they are geometrically, it's like a geometric sequence. They decrease by 2 every time. So you could also do, and each matrix is based on an expander code. So you could also do code switching with this. And it also, in a recent paper, Breaking Base, I meant to get the citation for it, and I didn't, but that's its name. They proved that actually the parity check matrix of Spielman's linear time encodable codes are, it's sparse. So it was already known that Spielman's Sipser codes, which have linear time decodability, has a sparse parity check matrix. But they proved that additionally, Spielman codes, which are the linear time encodable ones, also have a sparse parity check matrix. And so that can also allow for efficient code switching, because you can just prove that the code word times this matrix is equal to 0. And you can do that efficiently.
Spielman's paper is also an efficient decoder based on belief.
Yeah. So maybe you would think that the parity check matrix should be sparse, but I guess it wasn't proven before. But yeah, it does. It is efficient. You're right. It's linear time encodable and decodable codes. Yeah.
I think they're slightly different, the one in the Spielman paper and the one that they're used in practice, because, for example, the breakdown analysis cannot use.
Well, it's based on Yuval's paper, right, from DI 13.
Yeah, DI is definitely, we did not. DI is different from Spielman. There we achieve Gilbert. There the goal is to achieve Gilbert.
I see. Okay, you think the breakdown analysis is different?
Because you have to do the rewinding analysis because you cannot efficiently decode.
Oh yeah, that's true.
But that doesn't change the parity check matrix.
Yeah, that's true
You
too.
don't know how to decode, but a matrix.
But that is true. If Spielman codes are linear time decodable, why isn't the code that breakdown used decodable? Is it because they used the randomized version of Spielman's code or something?
Over the field.
It's over the large fields instead of binary. Okay, yeah. Okay, so this is taken from breakdown. Oh, sorry, I meant to cite breakdown here, but this was taken directly from the breakdown code, and they did this like analysis of the distance and the runtime and the rate. And so the rate is really good for Spielman codes. And the runtime is also good. It's linear time, but the distance is not so good. And so for REA, for message size greater than 2 to the 20, our distance is 0.19 with high probability, and it only uses 8n additions. One drawback of REA is that, well, so far we only have a distance analysis for large-ish messages above 2 to the 20. And I don't think Spielman has that same limitation. And that can just affect the shape of the interleaving. When I showed interleaved codes, the size of the row impacts the encoding time. And with REA, we need rows that are at least 2 to the 20.
So earlier you said that these non-foldable codes are usually more efficient for the first large message that you code, so that would be okay, right? Because you use it anyway on the first round when the message is large anyway?
Yeah, well, that's true. We are anyway encoding large messages. However, sometimes you can get a savings by, even if you have a large message, making the rows smaller, because it like depends on how you parallelize it or something like that. So that's kind of like an implementation detail. Okay, so quickly I'll go into trade-offs and open questions. So all of the trade-offs are some version of prover time versus verifier time in different manifestations. So we have, can we have a linear time encodable code with good distance? There's a trade-off, or like current trade-offs between linear time encodable codes and foldability. Foldable codes with small fields, and there's a trade-off between field size and proof size that is in the soundness analysis. Okay, so encoding time versus distance, these are benchmarks I took on a single core, comparing REA, Spielman, and Reed-Solomon. And as you can see, Spielman and REA are faster than Reed-Solomon, but they are not foldable, and their distance is worse. So both not foldable and worse distance means larger proof size. So as you can see, there's like a clear trade-off between prover time and proof size.
To what extent do you feel like the graph is architecture dependent?
Oh yeah, okay, that's it. And I forgot to mention another thing is that REA is just newly implemented and has not been optimized, whereas Reed-Solomons have been very highly optimized for decades. And REA is just something I personally implemented, kind of running up to a deadline. So definitely this isn't that reflective of how things are. And architecture specific, I'm not sure. This was on a pretty big machine just to handle the message sizes. But since it was on one core, the number of cores on that machine didn't impact it. But yeah, I'm not sure. I think it shouldn't impact it too much.
What's interesting is that read-sum involves field multiplication, whereas RA doesn't. And just like you talked about binary trees, and some architectures support it, some don't.
Yeah, that's true. Okay, and then this is the bottleneck of code switching. So as I was saying before, code switching benefits larger sizes. So these are benchmarks for Blaze, which is a recent paper of ours that uses code switching between REA and Reed-Solomon for a message size that it's not beneficial for. Like you wouldn't use it for this message size. I just wanted to illustrate. So the Reed-Solomon encoding and hash, as you can see, it's much slower than the Blaze encoding and hash. But the Reed-Solomon opening is much faster than the Blaze open. And the reason is because in Blaze, we are doing the whole code switching proof. However, when you get to larger sizes, that ends up being better. So the code switching thing becomes better for large sizes. But not for smaller sizes. And then finally, there is a trade-off that people don't really talk about, but between field size and proof size based on these soundness analyses. Okay, so one thing that is known is that Reed-Solomon codes have this better query complexity. So that's great. But then if you use this definition, which was introduced in DeepFry and then iterated on for the multilinear case, DeepFry is a paper from 2019 that was further analyzing these IOPPs. There's this epsilon, so the probability epsilon appears in the error probability and also in the query complexity. So if you want your probability to be really good, you can make epsilon bigger, but then your query complexity would suffer, and vice versa. And so there's a trade-off here where if your error probability is smaller, you can use smaller fields. Smaller fields lead to faster proving time. So in this sense, by tuning epsilon, you can actually make your prover time faster at the cost of your proof size, and vice versa. This is for all linear codes. Yeah, good question. This is my recent paper on this analysis, but it matches basic. This is like the multilinear version of the analysis in DeepFry. Yeah. Okay, so then open questions is: can we have linear time encodable code with good distance? Can we have a linear time encodable code with efficient local tests? It's kind of like foldability. And can we have an IOP for small fields? So for good distance, linear time encodable code with good distance, I think no. But I'm not sure. I don't think there are bounds on this that are proven.
With a linear time encodable.
Oh, really?
Yeah.
Oh, okay. So can we get...
Goswami indicates, Goswami indicates, I forget what they get. But I think it's not, I think these are linear time encodable, but in practice would not be.
Yeah, okay, so maybe in practice that are also fast in practice.
Yeah, Goswami indic definitely does not get the Gilbert-Rasham encodable.
Okay, so there is. Okay, so it's not an open question. Okay. Can we make it efficient is an open question. Yeah, so okay, I think the way I think about why it's hard to do this is because we want, if somebody's corrupted, you want to be able to recover the code, which kind of means that most of the code word elements should be functions of most of the message elements. So it seems hard that you could achieve that with a fast algorithm. Linear time encodable foldable code seems totally, I think, not possible because foldable codes are described in terms of this generator matrix, which are inherently quasi-linear time encodable. But maybe there's another way. Maybe with like really cool code switching techniques, we can kind of like achieve the same thing. And then because of this being the argument says, okay, it's based on the probability of sampling a random field element. The field size, we can really only do IOPPs of this type for large fields. So there's a way around that where you could do the encoding over a small field and then have the verifier's randomness be from a large field, but it would be cool to be able to do it for small fields.
What's the motivation for doing IOPP for small fields?
Just prover time. It will be faster. Yeah. And that is everything. Thank you.
Any additional questions? Okay, so then thank you very much, and we'll meet again at 11.
Great. Even if you guess and it doesn't necessarily mean